So I want to continue today to try to give a overall flavor or feel for three-dimensional manifolds and three-dimensional geometry. I think I want to maybe state some actual theorems, although the theorems aren't what's most important. The sort of point of view, I think, is what's most important. So to begin, I want to give some idea of what are all the possible examples of three-dimensional manifolds, and how close are we to really understanding all of them. So it's been known for quite a while. Well, there are quite a number of ways to generate all possible examples of closed three manifolds, but there's a particular way that is sort of visible. So this theorem, I'm not quite sure of the attribution. Licorice definitely proved it. I think Zisheng also proved this independently. So every oriented closed three manifold can be obtained. Let me put it this way. Any oriented closed three manifold can be obtained from any other one by removing a collection of disjoint solid toruses, or toruses, and gluing them back in by a different identification. So this process of going from one three manifold to another was explored by Dane. This process of removing a collection of disjoint solid toruses, people have started to call Dane drilling. You drill out holes and gluing solid toruses in. So when you drill, you have a three manifold, you drill out solid toruses, you obtain a three manifold whose boundary consists of toruses. And if you have a three manifold whose boundary consists of toruses and glue solid toruses back in, that's called Dane filling. And if you do it all in one step, first you drill, then you fill, but you don't stop for breath in between, that's called Dane surgery. And I don't recommend that you go to a mathematician for reconstructive surgery, but nonetheless, they profess to do it. Of course, there's general theories about surgery on general manifolds, but it has a particular different flavor for three manifolds. So in particular, where this is usually used is you start from S3, which is R3 union. It's the one-point compactification of R3. And take a collection of solid tori. This collection of solid tori is really represented by, there might be just one, so it's just might be represented by a knotted circle. I mean, it's actually interesting just to start with an unknotted circle. So you can think of thickening this to be a solid torus. You remove it, so you obtain a three-manifold whose boundary is a torus, and then you want to fill it back in. So how do you describe how to fill in a solid torus? I mean, suppose you have a three-manifold whose boundary is a torus. What are the possible ways to fill in a solid torus? Well, a key invariant of that is that on a solid torus, there's a unique homotopic class of simple closed curves on the torus that is the boundary of a disk inside the solid torus. And you can represent that simple closed curve by just giving, if you take a simple closed curve and lift it to the universal cover of the solid of the torus, it's always, then it lifts to something which is not closed. It lifts to a path, so it connects the origin to some pair of points of the form n over n comma m. And it's a standard, it's a theorem of topology, of two-dimensional topology, that any such curve is isotopic to a straight, something that looks like a straight line here. So really simple closed curves on the torus up to isotopy are in one-to-one correspondence with pairs of integers n and m, so that which are relatively prime. It's an interesting exercise in topology to show that you can't connect. Well, for instance, there's no simple closed curve that is represented by 2, 0 that first comes back to where it starts here. If you try to do this, then there'd be another copy of it like that, and it would cross, so it wouldn't be simple. In other words, you can't wind around twice, come back without crossing. Anyway, the pairs of integers which are relatively prime. And it's not, again, it's a theorem of two-dimensional topology, I guess, it's a theorem that a diffeomorphism of the torus extends to a diffeomorphism of the solid torus if and only if it takes the boundary of this meridian disk, it's called. The curve that bounds a disk is called the meridian. If and only if it takes a meridian to a meridian. It might, you can reverse the sign. You could take 1, 0 to minus 1, 0. You get that just by flipping the whole torus, solid torus over, like so. But so I'll just say that. So a diffeomorphism of T2 extends to D2 cross S1, the solid torus, if and only if it takes the 1, 0 curve to plus or minus 1, 0. So if you took the solid torus and glued it back in such a way that the diffeomorphism extended to the solid torus, then the three-manifold you get would be identical. You just use that extension to construct a homeomorphism for the three-manifolds. So the different three-manifolds you get are gotten by, it's really diffeomorphisms of the torus modulo those that extend, and those are exactly parametrized by pairs of relatively prime integers up to plus or minus 1. So Dane fillings, the process of Dane filling is parametrized by n, m relatively prime up to plus or minus, multiplication by plus or minus 1. Or another way to say this would be it's the rational projective line. Anyway, it's a slope it's a slope of a line. Or another way to say it is there's a line through the origin that passes through lattice points. Okay. So this is just to get started. So in other words, for each knot, for any knot, such as this knot, which, for any knot such as this knot, there's infinite number of ways to, if I drill out the knot and then plug it back in, I get it. There's an infinite number of constructions for three manifolds that on the face are probably, I mean, they're not obviously equal. If there are symmetries, if there are homeomorphisms of S3 which take the knot to itself, it might say that certain of these are the same, or it might not. I mean, in this case, can you see this knot has certain symmetries. Can you see a symmetry of the knot, a homomorphism of space that takes the knot to itself? You can think of drawing an axis that passes like that, passes between the strands at those places. And now does that work? Well, yeah, so you flip the whole thing over. This actually doesn't change the set of surgeries, though. So, I mean, anyway, there's an infinite number of fillings that seem to give different, that seem to, on the principle, give three manifolds. So one way to try to understand all three manifolds is first you try to understand all knots. I mean, or knots and links, so you can start adding other ones, and then you start to understand all fillings. Okay, so this is one reason. This is a reason why knots and links are important and significant for three-dimensional topology. And as I was saying yesterday, the geometrization conjecture is known to be true for link complements. So a link like this, for instance, has a hyperbolic structure. If I wanted, I could draw a picture of it on my computer and tell you what its volume is. I mean, I should be doing this in front of you, not hidden. I'm not even sure I want to do it. You have to believe me if I... The hard part is drawing the picture, so... Yeah, I can draw a picture of a knot, and it's an alternating projection. And now I just say hyperbolic structure, it's thinking. So it has a volume of 4.40083251612304. And if you drew any other picture of it with the other, it would always come out to be the same volume. I'd like to say a little bit about how you can actually find, how either by hand or by the computer can do it much easier than by hand, but how you can actually compute, assuming this has a hyperbolic structure, which of course it does, how you can actually find it. I want to give you some flavor for how that works. And then that also relates to the set of all Dane fillings, and then that relates to understanding all three manifolds and how they fit together. So I guess I'm going to start with I'm going to do a simpler example just to give some idea of, so this is, I'll do the example that was in the movie, but I'll describe it by a slightly different way. So here's an example of a link. This is made of three circles. This is called the Borromean rings, or Borromean rings, I think. Both pronunciations are sometimes used. They have the property that if you remove any one of them, the other two fall apart. Despite the drawing, it's not actually possible to make these out of round circles. It's interesting to try to understand why that's true, but it's not. I mean, anyway, they can be made out of ellipses, as you might have seen from the movie. Okay, so I want to describe how can you construct a hyperbolic structure for this complement of the link, and what does it look like? So one method was done in that movie, but I'll describe something else, which is in a way more direct. So the way that a computer might actually do it, or a person might actually do it, is you first decompose space. First, you take the complement of the knot or link, and you want to cut it up into pieces that you can sort of deal with. So to do that, I want to add some. What color will show up? This red might. Okay. First, I want to add some extra edges to make everything connected. So imagine you're making a model for a museum, and so then you. Of course, links won't just sort of float freestanding and without support. So add some extra supports like this to sort of hold them nicely. Now I want you to imagine taking little pieces of cloth, or take some kind of, well, maybe plastic is better. Anyway, you see there's a hexagon that you can trace out by going along one of these added red edges, along a piece of the knot, down on this red edge, along a piece of the knot, down the red edge, and along another piece of the knot. Okay, so there's one like that. There's also one here where you go down here, along, down, along, down, along, and so forth. And there's a whole number of these things, and there's one on the outside. Well, let's just concentrate on one for now. So it's like this. So if I think of fastening in a piece of plastic, clear plastic or something so you can see through it, like that, it's sort of twisted. It's like a twisted hexagon. So it's a hexagon where you twist three of the edges so they're vertical, and then you can glue them into place. And around this edge in the middle, four hexagons fit. Okay? And do this to all the faces. And now left over, really I might think of this link, I've drawn it on the plane on the plane of the blackboard, but you might think of it on the plane of the sphere. Think of taking the blackboard and twisting it. Conceptually, it's like this. You can think of these circles as if they're three great circles. So almost in the plane of anyway, it's like this. Anyway, there's also a giant hexagon on the outside, and you can make it close up. Just as these three great circles divide the sphere into 8 triangles, these divide, you get 8 hexagons like that. If you glue in all these 8 hexagons, it will divide space into 2 chambers, one on the inside and one on the outside, or one below the blackboard and one above. I mean, in this picture, it's one in the inside and one on the outside. You can't get, okay, it's now sealed. You can't get from the inside to the outside. Okay, now this gives a way to describe a combinatorial, it gives a combinatorial description of the three-sphere, of the knot complement, as obtained by gluing together two sort of figures. So if you take everything on the outside, you can think of this as being obtained, let's see. See, it's like the surface, seen from above, the surface, it looks almost like a sphere, but it's just that it's pinched together here where the red edge is. And at this red edge, it's pinched, at this red edge, it's pinched this way. At this red edge, it's pinched this way. So it's almost, the union of all these pieces of plastic is almost a sphere, but it's pinched. And seen from below, it's, you almost have a sphere, but it's pinched. So let's take take the region of space above here and unpinch it at those edges, and it's like that. It'll look like this. So I'm sort of flattening it out there. Now I have to flatten it out here. No, it goes this way. And so on. Well, I'll put this one down here. This is this is just the combinatorial pattern if I unpinch it. I can think of taking everything above the blackboard, divide it into this pattern. The only important thing is it's really made of 8 hexagons glued together in a certain way. The hexagons look like triangles, but these are vertices here. And I'm gonna take this, match it up with this figure, and then pinch together. To get this knot, I pinch together there. Does that make any sense? From below, there's a similar figure. Now remember, what I'm really trying to do is get the knot complement. I'm not trying to get the knot. So all these white things are parts of the knot. So I want to really eliminate them, make them go away. And one way to make them go away is to make them little. So I can take this picture, take this picture, and think of that picture with the white parts removed, and now collapse the white parts to points. And what I get in the end is, I guess I'll draw it on the surface of a sphere. It's the same figure of three intersecting circles. And I've just changed the sort of labeling so that the white edges which correspond to what goes to the knot are vanished. If I did it from below, it's perfectly symmetric. From below, I'll get another ball like this. Exactly the same. So what I claim is that, and really it's probably better to think of these as octahedra rather than spheres. I mean, it's the same thing topologically, but so I have two octahedra. And to obtain, so I claim that to obtain the complement of the knot, to topologically describe the complement of the knot in a sort of combinatorial way, I can take two octahedra, remove the vertices. The vertices correspond to what? To the knot, and I'm trying to get the complement of the knot. So I remove the vertices of these octahedra. And then there's some pattern of identification where each triangle here is glued to some triangle here. When I do that, and if I glue it in the right way, topologically I should obtain the complement of the Borromean rings. And you notice that, right, so each of these red edges has 4 pieces of this clear plastic coming down into it. So whatever pattern of identifications I have here, the edges will come together in 4s. So to make this in a geometric way, I want to have 2 octahedra where the angles are all 90 degrees. You can actually see what the pattern of identification is by staring at the knot. I mean, if you imagine, I mean, this knot, this link sort of suggests an octahedron. So think of an octahedron above, as suggested by the link, and an octahedron below. And initially, imagine them sort of, I mean, they're held apart by the knot, where one of them touches here, here, and here from above, and the other one touches from below. And anyway, because the knot is sort of, three-dimensional, they're held apart. But now, see, this edge of the knot slopes down from here to here, and down from here to here, and down from here to here. So just take these faces and twist them. I mean, you push this one down to the other one by twisting clockwise 1/3 of a revolution. You push this one down to the next one by twisting counterclockwise 1/3 of a revolution. It's just that, the pieces of the knot are just like threads of a screw or something. You just screw it together. And they alternate the way they do. And that's the pattern of identification. You can write it down. The computer can find this really easily. It's only when we insist on trying to visualize it that it's hard for humans. So the computer can take a knot diagram and very quickly find a pattern of identifications like this that gives rise to the thing. Now, how do you actually construct a hyperbolic structure for this particular link complement? Well, it turns out that if you take the Poincare ball model of hyperbolic space, inscribe a regular octahedron. I mean, in other words, put 6 points on the sphere that are the vertices of an octahedron. And now draw the hyperbolic geodesics. Joining them, somehow I've not made it symmetric enough. It turns out that all these angles are 90 degrees. Actually, one way to see this is that a plane in three-dimensional hyperbolic geometry, a plane corresponds to a segment of a sphere orthogonal to the boundary. And so these 8 planes of an octahedron correspond to 8 circles drawn on the on the surface of the sphere. And you can do it once you know that, you can do it very explicitly. Actually, the sphere maps to the plane by stereographic projection. You can make the angle of intersection of these circles is equal to the angle of intersections of planes. So here are 4 planes. I mean, this figure so far stands for 4 planes that intersect at 90 degrees. And now, I guess the other ones are like this. I'm not sure what I'm trying to prove to you by drawing the figure. Anyway, this figure here, I mean, these determine 8 circles on the sphere that are the exact solutions somehow for the 8 planes of the octahedron, and they all, I mean, around any vertex, I mean, like, this one makes a 90-degree angle to this one, which makes a 90-degree angle again to this one, etc. Anyway, this is how it turns out. So you should just take the most symmetric octahedron. Well, it had to be the most symmetric octahedron, and glue it together. It gives this hyperbolic structure for the complement of the Borman rings. So I want to say something about Dane filling. Well, it turns out there's a really nice way to compute hyperbolic, once you have a hyperbolic structure for a link complement, to compute hyperbolic structures for the Dane fillings, and it also gives a proof of a nice fact about them. So here we've obtained the complement of the link as a union of polyhedra in some way. You can always decompose a polyhedron into tetrahedra. So we could take this, we can take this octahedron, and you can add an edge down the middle, and then there's a tetrahedron with those 4. I mean, then there are 4 tetrahedrons sort of arranged around that edge. So the Borman rings is the union of 2 octahedra, which is the union of 8 tetrahedra. Now, the shapes of tetrahedron in hyperbolic 3 space are particularly nice. Essentially, one complex number describes the shape of a tetrahedron. Namely, if we again, we take the surface of we take this hyperbolic 3 space and map the sphere at infinity to the plane by stereographic projection. I mean, there's another picture of hyperbolic 3 space that this is related to, namely upper half space. So in other words, if you take a plane in R3, the region above it is one picture for hyperbolic 3 space. It's in fact just the sort of image of the ball essentially by stereographic projection. So every simplex in this picture can be arranged so that one vertex is up at infinity, one vertex is at 0, one vertex is at the point 1, and the other vertex is at some point which we'll call z. In this picture, a 3-dimensional hyperbolic simplex looks like this. And you can actually think of it, z, this number z is somehow an invariant associated, well, anyway, the z is a cross ratio of 4 vertices. There's a lot of symmetry to the picture in that if you take the common perpendicular, if you take any 3-dimensional, if you take a simplex in hyperbolic 3 space where it's all 4 vertices are at infinity, you take a common perpendicular to any 2 edges, then if you think of rotating 180 degrees about that common perpendicular. It takes this edge to the same edge in the opposite direction. It takes this edge to the same edge in the opposite direction. So it preserves all four vertices. So it's a symmetry of the simplex, and so so for any pair of opposite edges, you can interchange. You can rotate like that, flip two vertices. So that gives a group of order 4 of symmetries of the simplex. Anyway, this sort of explains the symmetries of the cross ratios. I mean, given each edge is of the simplex is associated with one cross ratio, which you can think of as the ratio of this vector to this vector. So this is like 1 over 1 minus z, and this is z minus 1 over z. And 1 over 1 and this is also z minus 1 over z, and 1 over 1 minus z. So each edge of the simplex is somehow labeled with a cross ratio, with a complex number, and there are the 3 cross ratios associated with this oriented quadruple of points. Now, how does this play into here? I mean, when it has, you have these 8 tetrahedra. Now, to get a hyperbolic structure, you have to give a shape to each of those 8 tetrahedra, so those shapes are given by 8 complex numbers. But around each edge, all the tetrahedra have to fit together and glue up. I mean, when you sort of glue them together, going around any edge, you have to come back to where you started. I mean, and that ends up being an equation that just the product of the cross ratios associated with those edges has to equal 1. So for each tetrahedron, you have a variable, a complex variable. For each edge, you have a very simple equation that a product of complex numbers equals 1. And those are precisely the equations to get a hyperbolic structure on this link complement. Well, it turns out when you carefully count equations in variables, you find that because of the Euler characteristic of a 3-manifold and various things. Anyway, it turns out if you have k components to a link, there are k more variables than there are equations. In other words, there's a k-dimensional family of solutions. I guess, so what I've left out is that ordinarily when just any hyperbolic structure on the complement of the link, it wants to be a complete hyperbolic structure. So when you glue these things together, if you're gluing non-compact spaces together, even if you glue complete non-compact metric spaces together by some identifications, it's not at all automatic that the result of the identifications gives you a complete metric space. And it ends up that exactly one of these ways of gluing gives a complete metric space. All the other ways, you get a k-dimensional family of metric spaces by gluing these things that are mostly not complete. And when you take the metric completions, the picture is like this. I mean, suppose we just have one. So suppose we just have one Is this what I want? No. Suppose we just have a knot. This is the figure 8 knot, I think. I mean, suppose we had a case where there's just one component. So I claim that in this case, if you look at these gluing equations, you'd end up having two variables in one equation. So there's like a one complex parameter. There's some algebraic curve. There's some one complex family of solutions where there's exactly one solution which gives a complete hyperbolic structure, and there's a nice, not smooth family of solutions in a neighborhood of that. If you take the metric completion of these various things, what happens is that there's a whole infinite set of these that give rise to hyperbolic structures which describe Dane fillings. So there's something like if you take the integer lattice and you sort of invert it, map it into this picture, a set that looks roughly like that gives rise to these Dane fillings. Anyway, the theorem, I'm trying to give some flavor for. Anyway, there's a theorem that if M3 has a complete hyperbolic structure of finite volume, but M3 has sort of K toruses at infinity. So it's like a link complement with K components. Then for each torus, I'll call it a torus at infinity, if you exclude a finite set of Dane fillings, all the rest admit hyperbolic structures. So, in other words, if I take something like the Borman rings, in this case, I think there's about, I forget the exact number, I think it's about 9. So for each of these circles, it may be more, maybe 10 or something. Anyway, there's some finite set which you can compute in this case of Dane fillings. So if you exclude those particular Dane fillings, so I choose an arbitrary Dane filling that's not one of those for this component, an arbitrary one that's not one of those for this component, an arbitrary one that's not one of those for this component. The resulting thing has a hyperbolic structure, and it's a hyperbolic structure, it's almost a trivial modification of the given one. It's gotten by just slightly changing shapes of these tetrahedron. It gives a metric space which is not complete. Take the metric completion. In the metric completion, you end up getting a circle where these links were, but the circle is somehow glued in a different way. In all the corners of the tetrahedra, these are really infinitely long sort of spikes on the tetrahedra. They're finite volume, but they're infinite diameter. They exponentially decreasing spikes. Anyway, these spikes end up spiraling around and converging toward those circles. Okay, I want to get on and say some more. So this is a basic relation, which I think, starts to give a sort of structure for all three manifolds. Okay, the volume is a nice invariant for three manifolds, for these hyperbolic three manifolds. Let me say something about it. So it turns out that one could give a purely topological definition. I mean, the definition is mostly due to Gromov with some extra tweakings or something. But there's essentially a topological invariant, or a topological definition for some invariant. This is the sort of Gromov norm for, it's defined for an n manifold, which ends up being a constant multiple of volume for hyperbolic things. So the definition is like this. You consider the manifold. I mean, one definition would be to try to, you see how many tetrahedra it takes to try to triangulate the manifold. So how many tetrahedra does it take to triangulate? And this is an upper bound for the invariant. I mean, this gives one kind of invariant, but this is not very nicely behaved under, so if you take a finite sheeted cover of a three manifold, you can certainly if you take an n sheeted cover, you can certainly triangulate it with n times as many tetrahedra, but or a k sheeted, finite sheeted cover, you can, given a triangulation here, you can lift it to a triangulation up here, but there might be simpler triangulations upstairs that don't come from anything downstairs. So so there's a modification of this definition that works well under finite sheeted covers, and it's like as follows. I mean, it's really, you look at one definition is you take the infimum of the L1 norm of a singular, in this case it's a 3 cocycle representing the fundamental class of a three manifold. But what this really means is that you think of, instead of using a whole number of, using whole tetrahedra, you can think of, I might try to cover the manifold by 1/7 of this one, and then 1/7 of another one like this, and then 1/6 of, you use fractions of tetrahedra, or fractions of triangles, but you just make sure that they add up right at each point. They have to add up to 1 everywhere. This is essentially what it amounts to. Okay, so then you ask what's the minimum number of things that you need to do that, but of course 1/7 of a tetrahedron only counts as 1/7. How many people can you fit in the car? Well, 5 1/4. Well, anyway, you're allowed to use fractions of tetrahedra in this case. Or I guess the usual thing is, 5 people. If each bus fits 20 people and you have 83 people, how many buses does it take? The answer is 4 3/20, or 4 remainder 3. the Gromov norm of a hyperbolic n-manifold equals the volume of the n-manifold divided by the maximum, well, I should say the supremum of the volumes of n simplices, which is always a finite number. So this says that the volume is essentially a topological invariant. It also says that if you have a degree 1 map from one manifold to another manifold, so I mean, here is an example of a, well, for a surface, by the way, this just gives the Euler characteristic, essentially. This Gromov norm is some multiple of the Euler characteristic. So if you can take a degree 1 map that goes like from a surface of genus 3 to a surface of genus 2 just by collapsing one of the handles. And it's obvious from the definition that this norm has to decrease under a degree 1 map. And with a little more trouble, you can show that when you do a Dane filling, the volume has to decrease. So a Dane filling is a little bit analogous to an example of degree 1 maps between manifolds. Anyway, the net result is the following. So here's a theorem. The set of volumes of hyperbolic 3 manifolds is a closed, well-ordered subset of the real numbers. Its order type, closed, well-ordered sets are up to isomorphism are called ordinals or something, or one definition of an ordinal. Anyways, order type is omega to the omega. For each volume, the set of 3 manifolds hyperbolic 3 manifolds with that volume is finite. It's definitely not always equal to 1. The finite number can grow with size. Okay, so a sequence of 3 manifolds has, well, if M sub I is a sequence whose volumes converge, then there exists a subsequence which are exactly of this type. They're Dane fillings. Dane fillings of a limit manifold. So you can kind of give a topology to the set of all hyperbolic 3 manifolds where you say that a neighborhood of, if you have a compact example, it's an isolated point. If you have a manifold with cusps, its neighborhoods consist of the sort of high coefficient Dane fillings on those cusps. And that topology somehow is described by the set of volumes. This sort of volumes is a sort of finite to 1 description of that topology. The order type is omega to the omega, by the way, because, well, see, if you have n cusps, it means it's look at fillings of one of them. If you take fillings of 1 cusp, that gives it ascending sequence, which has a limit. Then if you take fillings of 2 cusps, that's limits of things which are fillings of one cusp. So it's a double limit and so forth. So there are n-fold limits because you can have things with n cusps, n of these toruses at infinity. So of course, each ordinal has a name. There's some definite, I mean, you can give things, the volumes can be named by, things like, polynomials in omega. Like you could take omega 7th plus 8, omega to the 6th plus 5, omega cubed plus 156. So in principle, that describes some definite volume. In principle, I think it's even algorithmically possible to compute what it is. In practice, very few of these ordinals have been identified with exact volumes. Probably, I think it's pretty, I don't think it's quite proved, but very likely that the figure 8 knot is omega. The volume of the figure 8 knot is omega. Anyway, this gives kind of a structure for one can find. I mean, I can't say too much, I guess. I mean, I've said too much. But there are sequences of, I mean, to some extent, people have begun to get a feel for this. There are sequences of very nice links so that they're very rich in giving a large number of distinct manifolds by Dane fillings. And in principle, there's just some single infinite ascending sequence like that, things with more and more cusps that kind of control all other hyperbolic three manifolds. Now, whether this ever comes to be something that's really pinned down in practice, I don't know. But but in principle, many, many questions about three manifolds are probably algorithmically doable. It's just a question of whether they're sort of humanly comprehensible and doable. I want to say one thing, which is where you can get the software that, if you really want to look at examples of three manifolds, it's good to get the software that I'm using on my Macintosh. There's a program called SnapP. It's written mainly by Jeff Weeks with some other collaborators. And you can get it from ftp.geom.umn.edu. It's public domain software. So this is the Geometry Center in Minnesota. The best version is from Macintosh, but there are also versions that just run on the garden variety machine with a C compiler. And with it, you can do a lot. And I think ultimately, how do you conserve a theory of mathematics? I think it's a hard thing to do, but hopefully, I think there's a chance that somehow the computers will become the experts down the line when the current experts are all senile or dead or whatever. Thanks.
Are there any questions? If not, I'd like to thank Mr. Thurston for a very interesting sequence of lectures. I'm sure that, in particular, for showing us his view of the